for C, we're going to look at conditional probabilities and some formulas to calculate different probabilities. So, first thing, deciding whether an event is independent or dependent. So they are independent if one of them does not affect the other. Okay, so we have some examples here. Selecting a king from a deck of cards, not replacing it, and then selecting a queen. Those two events are dependent. And the reason they are dependent is because we did not replace that card. So I took a card out of the deck. That changes my probability of picking a queen from what it was the first time. Tossing a coin that lands on heads, rolling a die, and getting a 6. Those two events would be independent. Me flipping that coin has no effect on what's going to happen once I roll the die. Alright, driving over 85 miles per hour and getting into a car accident. Those are going to be dependent. The faster you are driving, the more likely you are to get in an accident. So when we are finding probabilities that are and, so remember we talked about this is the symbol for and. So the probability of A and B happening is simply the probability of A times the probability of B. So we're just going to multiply things whenever the question asks for and. So the probability of choosing a heart and a face card. So the probability of getting a heart would be 13 out of 52. That's how many hearts are in the deck. And the probability of getting a face card would be 12 out of 52. And then we are going to multiply those two numbers. And when I do that and simplify it, I get 3 over 52. So that is my probability of getting a heart and a face card. All right, when we have, this is another example for independent events, okay? The probability that a particular knee surgery is successful is 0.85, right? So 85% of the time, it is a success. So find the probability that 3 knee surgeries are successful. Well, the probability of the first one being successful is 0.85. All right, the probability of the second one being successful is still 0.85. And the third one is still 0.85 because these are 3 different people, so their probability of success is all 0.85. And we multiply those out, 0.85 3 times, and I get 0.614. So that is, there's about a 61% chance that all 3 surgeries would be successful. If I want to find the probability that none of the 3 surgeries are successful, so this is where we have to use the complement rule. So if the probability that it is successful is 0.85, the probability that it is not successful would be 0.15. So I'm going to multiply that 3 times because I want not successful, not successful, not successful. And when I multiply 0.15 times 0.15 times 0.15, I get 0.003. All right, so that is the probability of 3 people having this surgery and none of them being successful. All right, find the probability that at least one of the 3 knee surgeries is successful. Now, what we have to pay attention to here is this word at least. This is not saying that only one of the surgeries is successful. It's saying one of them or 2 of them or all 3 of them are successful. And so here is a little shortcut to figuring this out. All right, if I am having 3 surgeries, all right, 3 surgeries, I could have no surgeries are successful, so I could have 3 failures. I could have 1 surgery is a success and then 2 of them are failures. I could have 2 surgeries is a success and 1 failure. Or I could have all 3 surgeries being successful. So if the probability that at least one of the 3 surgeries would be all of these 3 together. Okay, so again, we can use the complement rule. I know the probability of 0 surgeries. We just found it right here, 0.003. So 1 minus 0.003 would be 0.997. So there is a 99.7% chance that at least one of those 3 surgeries, so 1, maybe 2, maybe all 3, all of those would be included in at least 1. All right, if we have dependent events, what this formula says, the probability of A and B when they are dependent is the probability of A times the probability of B given A. So knowing that this has happened, what's the probability of B? So we'll look at an example. It sounds complicated, but it kind of makes sense intuitively when we look at an actual example. All right, so 2 cards are selected without replacing the first card. Find the probability of selecting a king and then a queen. So what's the probability of getting a king? Well, there's 4 kings in a deck of 52 cards. All right, and then the probability of getting a queen, all right, would be there's 4 queens in the deck, but there's now only 51 cards. So that's what that Q given K means. It means I know that this one was a king, so now there's only 51 cards left in the deck because we're not putting it back. All right. So we multiply those two, and simplified, we come up with 4 over 663. So that's the probability of picking a king first and then a queen. Okay, the second thing that we're going to look at is whether or not events are mutually exclusive. And so mutually exclusive means that they cannot happen at the same time. So if I have one die, all right, can I roll a 3 and a 4 on the same roll? No, that is not possible. So these two events are mutually exclusive. It could be a 3 or it could be a 4, but it can't be both at the same time. All right, choosing a heart or a face card. All right, could I pick one card that is both of these, both a heart and a face card? Yes. All right, so these are not mutually exclusive because they can happen at the same time. So when events are mutually exclusive or not is important for when we're finding OR probabilities. So the probability of OR, A or B, is the probability of A plus the probability of B as long as those events are mutually exclusive. So if we go back to our dice example, these are mutually exclusive. So the probability of me rolling a 3 or a 4 would be the probability of rolling a 3 plus the probability of rolling a 4. So the probability of rolling a 3 is 1/6. The probability of rolling a 4 is 1/6. If I add those two together, I get 2 over 6 or 1 over 3. So I have a 1/3 chance of rolling either a 3 or a 4. All right. When things are not mutually exclusive, all right, we still add them together, but we have to subtract the overlap, the probability of A and B. That's what that is. Okay, so if we're looking at our card example, the probability that it is a heart, all right, heart or a face card. Okay, so it would be the probability of a heart plus the probability of a face card minus the probability of being a heart and a face card. All right, so the ones that are hearts and face cards. So hearts in the deck, 13 out of 52. Face cards in the deck, 12 out of 52. But there are 3 cards that are both hearts and face cards. So we don't want to double count those 3 cards because those 3 cards are included in these 13 hearts and these 12 face cards, and we can't count them twice. Okay, so 13 over 52 plus 12 over 52 minus 3 over 52, and we get 22 over 52, which simplifies to 11 over 26. So that would be the probability of getting a heart or a face card. So anytime things are not mutually exclusive, you have to make sure you subtract that overlap. Okay, and that is it for 4C.